Welcome back. This is Dr. Christy Patton-Lukes, and this time we're going to continue our discussion of mass and mole fractions. So what we had said last time is that the most common ways of talking about composition is going to be either a mass fraction or a mole fraction, and it's the mass of a component divided by the total mass, or the moles of the component divided by the total moles. We also said that weight and mass fraction would be the same. Then we had these facts, okay? One is the pieces of the whole have to add up to 1, okay? So the sum of x equals 1. And then the other was about when people talk about a percentage or a composition without being very specific. The assumption is that if they are talking about a gas, then they mean mole fractions. If they are talking about a liquid, it's a mass fraction. If they are available to ask, you ought to ask. But sometimes you've received, say, a request for a bid on something, and it's in writing, and you don't want to call them and ask this. So you can go ahead and get started and wait until you have some other things to ask them about. And then you sound like, oh yes, I knew that. So here's a problem. I don't want you to really do the math, but just let's think about this one for a little bit. So we've got a catalyst we're using in an automotive catalytic converter. So these use some very heavy metal kinds of materials in the catalyst. And this particular one has a mass fraction that is platinum that is 0.005, so 0.5%. And the rest of it is made up of aluminum oxide. So we want to know what's the mole fraction of platinum. And here's the deal. They gave us all these molecular masses of all the atoms. So I have aluminum oxide, so Al2O3, so 3 times 16 plus 2 times 27, okay, which is going to be 75 plus 6, so like maybe 130-ish, okay, just some mental math there, okay, and then the rest of it's platinum, which has 195 molecular mass, okay. Platinum has the highest value of the molecular mass. How is that affecting the mole fraction? It's going to turn out that it's going to make the mole fraction less than the mass fraction because of this higher value of M. So why? Let's look at an example and see why this would be. So if I want to convert between mass and mole fractions, it's really handy to assume a basis. Now you'll get more used to this, but a basis is on these problems where they don't give us, like they didn't say we have 100 grams of catalyst. If they don't tell us a starting amount, we can assume an arbitrary amount, and it'll make our calculations easier. And then at the end, I'm going to divide through by that amount, so it's not going to matter. All right, so let's look at air. Okay, it's roughly 79% nitrogen and 21% oxygen. That's on a mole basis because it's a gas. So if I assume that I have exactly 100 moles of air, then that would mean that I have 79 moles of nitrogen and 21 moles of oxygen. I can use the molecular mass. That would have units, if I'm working in moles, of grams per mole. So if I have moles, I want to multiply by grams per mole to get grams. Remember, those units have to be able to cancel top to bottom. So I get grams by multiplying the number of moles times the molecular mass. And this tells me how many grams I have of each one. So I have a little over 2,000 grams of nitrogen, around 700 grams of oxygen, making up a total of nearly 2,900 grams of air. If I want to turn that into a mass fraction, well, I just take the mass and divide by the total mass. So 2212 over 2884, and I get a mass fraction of nitrogen that is 0.77. I get a mass fraction of oxygen that's 0.23. So now if you look at these and relate it to that previous problem, the one with the heavier molecular mass, the mole fraction is relatively smaller than the mole fraction was. Okay? So This one I'm going to just suggest that you pause the video. I'm not going to work through it in detail, but I want you to try and do this one. So we have a gas that's measured in moles, and here's the compositional breakdown. And I want to know what the mass fraction of this that is CO2. So take a moment, pause the video. Alright, so here's the solution. I'm not going to go through this, it's very much like the last one. And I end up with mass fraction of CO2 is 21.9% CO2 in the total. Okay, again, pause the video and look at your work. Notice again, though, that I am using full sig figs in those intermediate calculations, and I only round to the 3 sig figs at the very last step. So sometimes it's really handy to be able to just know what the average molecular mass is of a mixture. Okay? If you have mole fractions, all you need to do is take the mole fraction times the molecular mass for each species, multiply them, and add them up. If I have mass fractions, well, remember the units on molecular mass are grams per mole, so I need to take the mass fraction and divide by the molecular mass. Unfortunately, when I do this, I get something that's not quite so pretty because the sum of those is actually the reciprocal of the molecular mass. So you're going to take the mass fractions, divide each one by the molecular mass, add them up, and then at the very end take the reciprocal again to get the average molecular mass. So let's look at a practice problem. 15% water and 85% ethanol by mass, and I want to know the average molecular mass. Okay, well, not really that hard, so I've got my sample, so I'm doing this not by the formula, but by logic. Okay, so if I take a basis of 100 pounds mass of the mixture, I have 15 pounds mass of water and 85 pounds mass of ethanol. The molecular masses are something I could look up, so 18 and 46. If I want to get to moles, I'm going to divide mass by molecular mass to get moles. So 15 divided by 18 is going to be about 0.83. 85 divided by 46 is 1.84. And I end up with 26.776 whatever pound moles. I can use that to get the average molecular mass by simply saying, oh wait, I want it to be something pounds per pound mole. So I have 100 pounds, and it was 2.678 pound moles. Therefore, the molecular weight, or the molecular mass, is 37.35. Now, from chemistry, you're probably also accustomed to talking about compositions in terms of concentrations. Okay? We will do that from time to time. It is not really as convenient for most of our problems to do that. You will find a few exceptions. So concentration is generally a mass concentration is mass per volume. Molarity, remember those? Oh yeah. It's going to be like moles per liter. So we'll use those, but we'll just use those in combination with densities and molecular masses to turn them into whatever we need for our problem. Now, one last topic here. Part per million and part per billion. Sometimes we're talking about teeny tiny quantities of chemicals, okay? Even a very, very small amount of, say, H2S is going to cause some serious health problems, okay? And so we tend to have environmental regulations that deal with these very, very small quantities. They tend to be based on part per million or even part per billion. They can be in either mass or mole fractions. Again, typically mass means it's liquid or solid. Typically mole means it's a gas, but it doesn't have to be that way. Now, if someone says that a mixture is 1.3 part per million A by mass, then what this is telling me is that the mass fraction is 1.3, and then parts per million translates to 1/1 millionth, so times 10 to the minus 6 kilograms of A per kilogram total, or pounds of A per pound total. When I have something that's in parts per billion, so 4.2 ppb, or part per billion B, okay, in the substance. So this, if you're in the US, that means it's 4.2 times 10 to the negative 9, because 10 to the 9th is a billion, okay? But if you happen to be in the UK someday, a billion is a million, so it's 10 to the minus 12th. These little cultural differences are going to suddenly show up in some really weird places that you were not expecting. So just to be aware of that there is not a universal definition of what a billion or a trillion actually is. So make sure that you know before you go, doing your computations. So just a little problem. An OSHA 8-hour limit for HCN, hydrogen cyanide, is 10 part per million. A lethal dose of HCN in air, according to the Merck Index, where they record these things, is 300 milligrams per kilogram of air at room temperature. So what we want to know is how many milligrams of HCN per kilogram of air is this 10 ppm? So what fraction of the lethal dose is this? Okay? So turn one of them into the other one. So 10 ppm is 10 times 10 to the minus 6, or 10 divided by 10 to the 6th. Okay? And now then, I just simply need to turn these things from, these are gases, right? So I need to turn these into mass fractions instead of mole fractions. So I'm going to need the molecular weight. So if you play the game, check those units. Notice that every time I write moles or grams, I'm always writing grams of what, moles of what. Okay. Turns out that this one is 9.32 milligrams of HCN per kilogram of air. So this is, the regulation is that there's only 3% of the lethal dose. So I'm actually kind of happy with this answer because it reassures me that the EPA is looking out for us and they're not going to let us get too close to that lethal dose. So again, work on these conversions. This is usually the first sticky spot in the course for most people. So practice it because it's going to keep coming up. Okay? We're going to conclude this chapter in the next 2 lessons looking at temperatures and pressures.